All right, so we are starting lesson 3.3, or it's like unit 3, lesson 3, which is on synchronous counters. I am actually recording this on March 9th of 2022 for what will happen as a lesson after the break. So probably I'm not going to remember any of this because it's going to be like a whole week. I'm going to be like, what was that lesson about? Oh, synchronous counters. So anyway, it is synchronous counters, small scale integration. So we're looking at SSI. So how to build the counters using flip-flops and going back to those JK flip-flops. So we'll go over, well, let's click on the next slide. So we've got our presentation topics there, defining what a synchronous counter is, providing examples of 3 and 4-bit up and down counters, and basically they're the same thing. You just add an extra flip-flop and an extra AND gate to the design to go from a 3-bit to a 4-bit. So we won't spend too long looking at the differences between those two. All right. So here's the deal defining a synchronous counter. We did asynchronous counters, and we know that the prefix a means not. So asynchronous is not synchronous. And we know that an asynchronous counter is called that because not all of them are synchronized with the clock. Only that first flip-flop is clocked with an external clock, and then the rest of the flip-flops are clocked from the previous one. In a synchronous counter, all flip-flops are simultaneously clocked by an external clock. So you got synchronous, we got what do we have here? Looking for that button. There we go. Synchronous and simultaneously. So synchronous at the same time, they're all going to clock together. Synchronous counters are faster. So we're looking at the, well, that was horrible. Try that again. We'll do a highlighter. We're going to highlight a couple times in this PowerPoint. So are faster than asynchronous counters at simultaneous clocking. So that's because you don't have that ripple effect. Synchronous counters don't suffer from the ripple. Okay, so you're not going to get those like weird other numbers in your count. But they require more logic than asynchronous counters do. So they're a little bit more complicated in their designs. We have a list of pros and cons there for them. Okay, so this one has animation. Hopefully I don't mess it up. So this is our 3-bit sync up counter. I don't sync up counter. I don't know. This is going to duplicate a slide that's later on, but pretty much what you've got here is you've got your clock, okay? And you can tell from where I'm looking is that we're clocking on the falling edge. Okay, and so this is 0, 0, 0 because all of them are low, and then we move to 0, 0, 1 because that one goes high, and by the time you're done, you're at 1, 1, 1 because they are all high. So we're counting from 0 up to 7. What you want to note here, though, is that this one triggers, the Q1 triggers on the falling edge, but both of the previous ones have to be falling. And if you can get that, then the design of how the synchronous counters are put together is going to make more sense. And then when we get over here to the third one, that's like going to be triggered on the falling edge of all 3. So the first one is triggered or toggles whenever there's a falling edge of the clock. So if I point to it, so we have a falling edge, and then on the next falling edge it toggles, and the next falling edge it toggles. And so this one is toggling with every falling edge of the clock. This one, Q1, is toggling when both are coming down. So if it's just the clock that's coming down, then Q1 is not toggling. That one toggles when both Q0 and the clock. And then Q2 toggles only when all 3 of them are coming down. And so this one here, Q2, does not toggle when the clock and Q0 are falling. So that gives you, like, when you can kind of get that idea, that's going to help us with our design. So I think when I click on this, we're going to get the animation. Okay, that's beautiful. You know what I should do is I should erase my stuff to clean it up so that you can see their animation. Their animation is probably cooler than mine. Anyway, okay, there we go. So we've got the toggling on the falling edge of the clock. Q1 toggles when both Q0 or Q0 and the clock are toggling, and Q2 toggles when all three of them are toggling. So I guess that was pretty cool animation. I guess see all that toggling going on. Okay, so this is how it is designed, and I want to park on this slide for a little bit because if you understand how the wiring works, then of course you're more likely to remember how to wire them and not make mistakes and have to rewire stuff. So here is Q. I don't like that highlighter. I'll try this one. Okay. Q0. Okay. Now let's look at a couple of things first. Let's look at the clock. So the clock, if you look at the clock, is running into all three of the flip-flops. And I am going to unhighlight that. I just want to draw your attention to it so that you can see it. So that's what we mean by that synchronous counter. All three flip-flops are toggled or are tied to the external clock. Okay. Now, notice in the first flip-flop, so we have our 5 volts, and then just notice that the 5 volts is going to the presets and the clears of all of our flip-flops. Okay, I'm going to get rid of that too. That means that we're not using a preset, or we're not using a clear for this particular design. So all of those are active low, and we are tying them to 5 volts. Okay, so let's get to the actual clocking part. So when you look at the first flip-flop, if you look at J and K, both of those are tied directly into the 5 volts, which you may or may not remember is toggle mode. Okay, so that means that that is set to toggle. That looks like togote. That is the word toggle. G-L-E. Okay. Nope, not any better. I give up. Not any better. So when you tie both J and K high, that means that flip-flop is set to toggle. And the other options are like no change, set, and clear. But we want the flip-flop to just toggle. We want it to go on and off, and we want it to go on and off every time that clock goes. So first flip-flop is tied to the clock, and it's in toggle mode, which means every single time that clock hits that falling edge, okay, this guy is going to turn on and turn off. Now, let's look at the next flip-flop. So we're going to go look at the JK on the flip-flop. So there's J and there's K. Okay, and you can tell they're tied together. And we're just going to follow that. Okay, so that is actually tied to the output of the previous flip-flop. So remember that this flip-flop here is toggling on and off with the clock, okay, with just the falling edge. So this means first falling edge is going to turn on, second falling edge it's going to turn off, and only on the second falling edge, because remember it's a negative edge trigger on this, will this be going from will this both be high? Okay, so we have like high, oh my gosh, okay. First falling edge, this is going to go high. On the second falling edge, this will be high, which will set this into toggle mode, which means this is going to toggle. Then this is going to cycle off. So on the next falling edge of the clock, this is going to be set for no change. So this is like important to remember. The JK flip-flop, when it's 1-1 is toggle. Let's see if I can write the word toggle. When it's 0-0, it is set for no change. And so when this first flip-flop it is off, this one here is set for no change. And so that one there isn't going to change at all until the clock toggles again, turns this one on, and then on the next falling edge, then this will toggle. And that's what gets you that every other toggle. Hopefully I explained that clearly enough. So because this is tied to the output here, this flip-flop is going to be going back and forth between toggle mode and no change, where this one here is constantly set in toggle mode. This one is going back and forth. Sometimes it's in toggle mode, sometimes it's in no change mode, and it's only going to toggle when it's in toggle mode, which is going to change with the output of the first flip-flop. Okay, so that brings us to the last one. if you need to go back and rewatch that, or you basically are like, I watched this video from home and that was a hot mess, Miss Taylor. Can you please explain that in class? I will do that. Just let me know. Okay. So the next one, we need to look and see where are these inputs coming from. So both of those are coming from this AND gate. So that is going, remember, it needs to be in 1-1 to toggle. So that is going to be high in toggle mode when both of these are high. Those are both of your inputs to the AND gate. So we need to find out, okay, well, where is that AND gate coming from when both of those are high? One of them is coming from the output of the first flip-flop. The other one is the output from the second flip-flop. So this one, the last flip-flop here, is only going to be in toggle mode when both of, good heavens, when both of these are high and end up toggling, well, when they're both high and then they, on the next toggle of the clock, are going to go low. But both of them have to be high. And that's pretty much the wiring there. And then when we look at the 4-bit, you would have another flip-flop down here, and you would have like this output running with another AND gate that would be tied to the output of the third flip-flop. I think PLCW uses a 3-input NAND there, or you can use the existing AND and just put another AND on there for that new output. Okay, so this should make a little bit more sense now that you've seen we've got the wiring diagram here. So the first, remember this first flip-flop here, Q0, is constantly in toggle mode. So that's why it toggles on every single falling edge, okay? We're kind of tracing that through there. The second flip-flop, though, is tied to the clock and to the first one. And so the inputs to put it on that toggle mode, it's coming out of that first flip-flop. So if the first flip-flop is low, it means the second flip-flop is in no change mode. It's not in toggle mode. Once that first flip-flop goes high, that sets the second flip-flop into its toggle mode so that when the clock drops low, it's going to make the second flip-flop go high. As long as this flip-flop, flip-flop 3 there, or Q2, is in no change mode, so it's not going to toggle at all, that will only go into toggle mode when both of these inputs are high. And so you're going to take these two inputs, run them through an AND gate, and then feed those into JK for that third flip-flop right there. Okay, and then when these are both high, it's going to put this flip-flop into toggle mode so that the next time the clock falls, this one will toggle up. And then this won't be in toggle mode again until we get down underneath my head there. Again, for the 4-bit counter, you just add that extra flip-flop on. So that first one was the one I wanted to spend the most time on because I wanted to kind of go through the wiring on that. Notice that your Q knots here are not tied to anything, but we would use that if we wanted to make a down counter, which is like the next slide. So if you wanted to add that first flip-flop, you've got two options. You can use a 3-input NAND or AND gate here and just run all 3 of those into it so that, yeah, it'll go into toggle mode when all 3 of them are high. Or you could take the output from this one, which would be the first 2, and then AND that with the third one. Probably that's more efficient design because this would require a totally different chip to do the 3 inputs. So it would make more sense to do that with 2 AND gates there. Okay, and then this is our down counter theory. So we're starting at the 1, 1, 1 and counting down to 0, 0, 0, which you can totally see underneath all that animation there. It's really the second half of this lesson can go a lot faster because it's the same thing, except now you're just counting down instead of up. We've got the same issues with like the falling edge. So every single time that clock falls, you've got Q0 or Q0 toggling. This is going to be tied to an AND gate here so that it will toggle on the falling edge of every other one and so forth. So here's your circuit diagram, and the AND gate now, notice this is tied to Q not, and that is what makes it your down counter. So we have covered that before, because in order for this to go into toggle mode, okay, because we're counting down, if you tie it to the outputs, it won't be in toggle mode at the right time. So you need to tie it to the not, and that's that like opposite polarity or same polarity as the clock. Like, so yeah, so that's your down counter, and just make sure that you're making note of that, you know, whether you're designing an up counter or a down counter and how to change it. And it's the kind of thing that's easy to forget, and like I'll forget it if I don't do it hardly ever. So yeah. And then adding the extra flip-flop there, you add the extra NAND, or I don't know why I keep saying NAND gate, I'm in NAND gate mode, AND gate there, and again, you're tying it to the Q0 instead of to Q in order to create your down counter. So that's pretty much the entire lesson, and I will let you know what in the activity I want you to do with the SSI. We're going to move through the counters fairly quickly. I do want to get to state machines before you guys take your finals. So that's kind of my goal, and that's the first lesson in Unit 4 is to get to the state machines. So we've got to do some stuff with MSI, synchronous counters, and then the 60-second timer project, and then we'll get into the state machines. And what would be cool to do, well, you know what, I'm not going to talk about it in this video. So, okay, so let me know if you have questions, if I really bungled something, or you just need clarification, or you need to walk through an example like in person instead of in the video, and that's totally fine. Just let me know if you need to do that, and I hope this video helps.